I'm back again to take a look at the next 5 questions from the individual competition at the Math Olympics hosted by UNF. We're going to start with number 6. Number 6 asks us to determine the area bound by the curves y equals x squared minus 1 and y equals 2x squared plus 2x minus 1. So to find the area between two curves, we're going to use this format. We need to find the integral from a to b of f of x minus g of x dx. This will give us the area between these two curves as long as f of x is greater than or equal to g of x. So what I like to do is start by drawing a graph of these two curves so I can decide which curve is the larger curve. F of x is going to be my top and g of x my bottom. So y equals x squared minus 1 is straightforward to graph. A little bit harder to graph is y equals 2x squared plus 2x minus 1. I'm going to rewrite this in vertex form by factoring out a 2. I can complete the square. I'm going to take the coefficient on the x, which is 1, half it, and square. That's the number that I'm going to add to the parentheses. So starting with 1, half of 1 is a half. 1/2 squared is a quarter. So that's the number I need to add to complete the square. I need to balance that out by subtracting 1/2. So by distributing 2 times 1/4, I've added 1/2 to the overall function. I need to subtract 1/2. So now that inside will factor to be x plus 1/2 squared. And I'll combine -1 and 1/2, so that's a -3/2. So now I have a better sense of what that graph is going to look like. It has a vertex of -1/2, -3/2. The vertex of -1/2, let's say this is 1, -1/2, and -1/2 would be here. And the other curve, x squared minus 1, looks something like this, shifted down 1 unit. The other curve is a little bit skinnier. So the other curve is a little bit skinnier because of this coefficient of 2. And it's a little bit hard to see the picture right now, so I'm going to get a little bit more information before coming back to that graph. So I need to find the intersection points that will help me find the bounds on this interval, the a and the b. So I'm going to set these two equations equal to each other to find those intersection points. X squared minus 1 equals 2x squared plus 2x minus 1. I'm going to collect all the terms to the same side, subtract x squared, add 1. I have 0 equals x squared plus 2x. If I factor out an x, that would leave me with x plus 2. And I'll set each of these factors equal to 0, and this tells me where my intersection points are at 0 and -2. And so that's probably why I'm not seeing my full picture here, because the other intersection point is way off over here. So let's see if I can get a little bit better picture. -1, -1, -2. My first curve would have these points right here. This is the curve y equals x squared minus 1. The other one will have that vertex at -1/2 and -3/2, so somewhere around here. It intersects at 0. So at 0, it'll intersect with this point right here, 0, -1. And I'll try to be symmetric onto the other side. And my other intersection will happen at 2. I'm not sure what that y value is right now. But it was important to see this so that I can see that y equals x squared minus 1 is the top curve, and the 2x squared plus 2x minus 1 is the bottom curve. So now I'm able to set up my definite integral with bounds using this lower bound of -2 and the upper bound of 0. We're going to integrate from -2 to 0. X squared minus 1 is my top curve, minus 2x squared plus 2x plus 1 dx. Let's do some algebra to clean up inside the integral. And I'll have x squared minus 1 minus 2x squared minus 2x minus 1. That's a negative x squared minus 2x dx. And I'll find the antiderivative. I'm using the fundamental theorem of calculus. Find the antiderivative negative x cubed over 3 minus 2x squared over 2, and we'll evaluate that from -2 to 0. So we get big F of b minus big F of a, -0 cubed over 3 minus 2 times 0 squared over 2 minus, I can simplify canceling those 2's, F of -2, I have -2 cubed over 3 minus -2 squared. I have 0 minus -2 cubed is -8. -8 times a negative, +8 over 3 minus -2 squared, that's 4. So we have -8 over 3. We get a common denominator. That would be 12 over 3. So 8 over 3 minus 12 over 3 would be -4/3. With the carry down the negative out front, we have 4/3. 4/3 for our area between the two curves. Our next question says a cannonball is shot up in the air and its path is modeled by a quadratic function y equals f of x. In this model, the cannonball starts at the point 0 and 7/2 and it heads to the right. It reaches the highest point at 3, 8. What are the coordinates of the location of the cannonball when the height is 0? So this question tells us that the path of the cannonball follows a quadratic function. So it's really helpful to know what formats the quadratic functions take. That's f of x equals a times x minus h squared plus k. And hk is the vertex, and it's also the highest point. So right here, when it reaches its highest point, that's indicating what the vertex is, 3, 8. And then we're also given this other point, the starting point, which we can consider to be the x, and the y. So we can substitute for hk for the vertex and substitute xy, and we'll be able to solve for what's missing, and that's our value of a. And once we know the value of a, we'll be able to find the other points along this cannonball's path. So I'm going to substitute 7/2 in for f of x. I don't know a. 0 in for x. We got for the vertex 3 and 8. Now to solve this equation, we have 7/2 equals a times 0 minus 3 squared. That's 9. 9a plus 8. I'll subtract 8 on both sides. And if I find a common denominator, that's negative 16 over 2 plus 7 over 2. So that's a negative 9 over 2. On the other side, we have 9a. When we divide both sides by 9, we get a is equal to negative 1/2. So now we know that the path of our cannonball is modeled by negative 1/2 times x minus 3 squared plus 8. So we want to find out what are the coordinates when the cannonball has a height of 0. So that's height will be the y portion. I'm going to set this function equal to 0 and solve the equation. I'll subtract 8 on both sides. So negative 8 equals negative 1/2 x minus 3 squared. I'll multiply both sides by the reciprocal of negative 1/2, which is negative 2. I have 16 equals x minus 3 squared. I can square root both sides. And that gives plus or minus 4 equals x minus 3. I'll add 3 to both sides. And I have x equals 7 or negative 1. 3 plus 4 is 7. 3 minus 4 is negative 1. So we're going to answer the coordinate 7, 0 matches a height of 0. For number 8, we need to pick a 3-digit code. The digits range between 0 and 9. One of the digits must be a 3, and all of the digits must be distinct. How many different 3-digit codes satisfy these conditions? One of the things that's going to help us with this problem is called the fundamental counting principle. And it says if we can break this down into different parts, then we can count how many options are for the parts, and we multiply all of those together, all the parts together. So we have a 3-digit code, and for that 3-digit code, we know one of the digits must be a 3. So if we think about the 3 different options for that, the 3 could go in the first position, in the second position, or the third position. So if that 3 goes in the first position, I know that I have 9 other choices for the second position. So I think I need to rewrite this a little bit. So instead of writing the number 3, what I want to do is write the number 1. And the reason why I'm writing the number 1 is because that's only one choice. So I'm counting the number of options for that position. So if I put a 3 in that first position, that is the only choice for that position, so that's a 1. And I can have the 3 in the second position or the 3 in the third position. Then, back to what I was saying before, I have 9 different digits that could be in that second position. I know it's 9 possibilities instead of 10 because it says that all the digits must be distinct. Okay, so then for this last position, I only have 8 choices because that has to be different from the other 2. So we have 9 choices and 8 choices for each one of these options. So if I multiply them together, that gives me 72 options if 3 is in the first position, 72 options if 3 is in the second position, and 72 options if 3 is in the third position. We'll add up all of these possibilities, and we get 216, is that right? Yeah, 216. Yeah, 216. Now there is another way to do this. What you can do is you can say that I don't have any choice on one of the positions. I have 9 choices for the other position and 8 choices for the third position. And then I have 3 different positions for the 3. So that will also give you the 216. For number 9, the tangent line to the curve y squared equals x cubed plus 1 at the point 2, 3 intersects the curve at a second point. What is this point? So let's take a look. The tangent line to a curve, I need to find that. I know that the derivative is the slope of the tangent line, so I'm going to calculate the derivative of y squared minus x squared plus 1. Now this equation is not written in explicit format, it's written in implicit format. So I'm going to calculate the derivative implicitly. I'm going to calculate the derivative on the left-hand side with respect to x. I'll calculate the derivative on the right-hand side with respect to x. Now on the left-hand side, because the variables don't match, I need to make sure that I'm calculating the derivative with the chain rule. So the derivative of y squared is 2y, and I'm going to chain by multiplying by the derivative of y, dy dx. On the right-hand side, the variables do match, so I'll calculate my derivative in the straightforward way. Derivative of x cubed is 3x squared. Derivative of a constant is 0. I can solve for the derivative by dividing by 2y on both sides, and now I have dy dx, or if you want to think of this as y prime, being 3x squared over 2y. So this allows me to get the slope of the tangent line at the point that we're interested in. So that slope at 2/3 will be 3 times 2 squared over 2 times 3. Simplifying, we have 2 squared is 4 times 3 is 12, and 2 times 3 is 6. We reduce that down to 2. So now I have the slope of the tangent line. I can get the equation of the tangent line with algebra. I'm going to use the point slope form, y minus y1 equals m times x minus x1. I'll substitute in the slope of 2 and the point 2, 3 into x1, y1. X minus 2 and y minus 3. So I'll solve. y minus 3 equals 2x minus 4. I'll add 3 to both sides. That gives y equals 2x minus 1. So now I have the tangent line. Now, it says that this tangent line intersects the curve at a second point. So now I want to find the intersection between this tangent line and the curve we're talking about. So I'm looking for the intersection of y equals 2x minus 1 and y squared equals x cubed plus 1. So find the intersection. I will substitute 2x minus 1 into the other equation. That gives 2x minus 1 squared equals x cubed plus 1. Simplifying, I would have 4x squared minus 4x minus 1, that will be plus 1, equals x cubed plus 1. I'll move all the terms to the same side, and that will give 0 equals x cubed minus 4x squared plus 4x. You can solve this by factoring out the x, have x squared minus 4x plus 4. This factors into x minus 2 squared. And I can set each of these factors equal to 0 to get x equals 0 and x equals 2. So I already knew that the tangent line intersected at 2 because that was the given point of the tangent line. So the other point is 0. And I need to find the ordered pair. So I'm going to substitute this back into the tangent line. Y equals 2 times 0 minus 1, and that's negative 1. So the point, the second point that our tangent line intersects is the point 0, negative 1. In this question, I want to solve the following equation. 2 natural log of 2x plus 1 minus natural log of x plus 8 equals natural log of x. So this is a logarithmic equation, and I notice that I have logs on both sides. When you have a log equals a log, what's inside the log must be equal to each other, as long as the base of the log is the same. All of these are natural logs, so they're base e. So that's the strategy that I'm going for. I'm going to write a single log on the left-hand side and a single log on the right-hand side so that I can equate what's inside the logs. Before I can write it as a single log, I need to review a couple log properties with you. So we have the product rule of logs. You can write log base b of m times n. So if you have a product inside the log, you can write it as the sum. That's log base b of m plus log base b of n. Then we have the quotient rule for logs. If you have a quotient inside a log, log base b of m over n, you're going to subtract the logs, log base b of m minus log base b of n. And then we also have the power rule of logarithms. If you have log base b of m to a power, you can move that power to the coefficient. So we have p times log base b of m. So we're going to start on the left-hand side by using that power rule, bringing the coefficient into the exponent. We have natural log of 2x plus 1 squared minus natural log of x plus 8 equals natural log of x. Then we have a subtraction. So we're able to use the quotient rule for logarithms. That's natural log of 2x plus 1 squared over x plus 8 equals natural log x. Now we have a single log on each side. We can equate what's inside those logs. That gives us the equation 2x plus 1 squared over x plus 8 equals x. So to solve this, I'm going to get rid of the fraction by multiplying both sides by the denominator. That gives 2x plus 1 squared equals x times x plus 8. Let's do a little bit of multiplying. If I multiply out 2x plus 1 squared, I get 4x squared plus 4x plus 1. If I distribute the x, I get x squared plus 8x. I'll move all the terms to the same side, subtracting x squared, subtracting 8x, and that gives 3x squared minus 4x plus 1 equals 0. I can factor. If I factor, I'll have 3x and x, 1 and 1, and we need both of these to be negative. I'll set each of these factors equal to 0, and I get proposed solutions of 1/3 and 1. And the reason why I say these are proposed solutions is because logarithms have restricted domains, so we need to check to make sure that these values are in the domain of our log expressions. So if I were to substitute a 1 in for x, that would be 2 times 1, which is 2 plus 1. That is a positive number. Log of a positive number is defined. If I substitute a 1 in for x in the second expression, 1 plus 8 is 9. Log of a positive is defined. If I plug a 1 in for x here, I once again get log of a positive, which is defined. So then on 1/3, 2 times 1/3 is positive, plus a positive, that's okay. 1/3 plus 8, that's okay. And then 1/3 over here. So I've got two solutions, 1 and 1/3.